Hello, everybody. Oops, the mic's crooked. There we go. All right, we are starting our first kind of major topic in this section, dealing with something called infinite series. So the last section dealt with sequences, which set up infinite series, but series are really what it's all about. So before we get into what a series is and the examples that you need to be able to do, I need to show you this proof to establish a very important idea and get some notation out of the way. So here is the intro. Do you believe that 1/3 equals 0.3333333 repeating? How do you have something that goes on and on forever equaling an actual value? Is a weird idea in math that's going to be a major part of this whole section. So I'm going to show you that this is actually true by doing a little mini proof. So we can start with the idea that, okay, let's assume this is true. 1.03 is equal to 0.3 repeating. Okay, if I multiply both sides of the equation by 10, I would get 10/3. And I would get, when you multiply by 10 and you have a decimal expression like this, you move the decimal one time. So 0.3 repeat. If I subtract both sides of the equation, kind of like when you're doing elimination, so 10/3 minus 1/3 is 9/3. And then here's kind of an interesting idea that happens on the right. The 0.3 repeating and the 0.3 repeating pretty much just cancel out. And 3 minus 0 is 3. And does 9/3 equal 3? It does. So we've established that, yes, we started with the premise, is this true? And we came to a true conclusion. So in other words, it is true that 1/3 equals 0.3 repeating. So why did I show you this? Well, there's another way to think of 0.3 repeating. You could think of it as 0.3 plus 0.03 plus 0.003 plus 0.0003 plus on and on and on. If you were to sit there and add this up in your calculator, you'd get 0.333333 for as many times as you're including the terms. And that does, in actuality, equal 1/3, as we just proved. So you have something that is infinite, or an infinite, there's the key word, an infinite sum. An infinite, that's not right. Try this again. Infinite sum equals a finite value. That is going to be a major, major part of this section of the course. Can you have something infinite that you're adding together equal a finite value? Yes, you can. Now, we're not going to want to write it out as this something plus something plus something. This is the expanded out. So the first thing is I want to show you that we can rewrite this using something called sigma notation. So what is sigma notation? Sigma notation, I'm actually going to show it to you and show you why it works. This is called sigma. It means sum. It means you're adding together. And the bottom number tells you the variable, so n equals 1. And the top tells you when to stop. So let's say I told you this was the sum we were adding together. So let's go 3 and then 0.1 to the nth power. Okay, so we're going to have to start getting used to working with this idea called sigma. What on earth is this saying? Here's what it's saying. It's saying plug 1 in for n, just like we dealt with sequences. So when we had a sub n, you plugged in 1, you plugged in 2. That's the same thing we're doing here. You're going to plug in 1, you're going to get 3 times 0.1 to the first, 0.1 to the first, which is 0.3. Plus, the sigma means, okay, now that you've done 1, move on to the next number, which is 2. And now plug 2 in. And you're going to get 3 times 0.1 squared. 0.1 squared is 0.1 times 0.1, which gets us 0.01. And then times 3, 0.03. And then continue that process by then moving on to the next. So, 3 times 0.1 squared. Plus, now move on to the next term, 3, and plug 3 in to the series and get that same value that you got the previous few times. So 0.1 cubed, which is 1/1000th, times 3, which is 0.003. How many times do you do this? You would do it with 4, you would do it with 5, and then you'd stop. The top number tells you where to stop. So this is not an infinite series. This is called a finite series. And there are 5 terms: the first term, the second term, the third term, the fourth term, and the fifth term, which I did not write. And you get an actual answer. All finite series have answers because then you can just add them together because there's a stopping point. But the key in this whole section is we are very rarely going to deal with a finite series. We're going to deal with something called an infinite series, where the top bound is infinity. And you just keep doing the process over and over. And the key component is going to be sometimes these series converge to a value, meaning you get an answer. Like in this case, this series converged to 1/3. And other times you're going to get diverges, meaning it did not converge to a value, and we will see both of those in a second. So this is hugely important. An infinite sum that equals a finite value or number is the same as saying the infinite series converges to that value. You have to start getting used to this new way of speaking about these things. So very rarely do we say the infinite sum equals a number. We will, but the more common way we're going to start to do it, especially when we get to something called Taylor series, is we're going to say the infinite series converges to this value, whatever this value happens to be. Right, so sometimes they converge and sometimes they diverge. And just like in the last section, that's really all we're trying to do right now. We're trying to establish, does a infinite series converge or diverge? So I think this example really helps to lock it in. 2 competing examples. Let's take a look at 2 different infinite series, one of which will converge and one of which will diverge. So we have this one, n equals 1 to infinity. Let's do 1/2 to the n. By the way, I'm using n. I'll also use k a lot here. So n and k are kind of the 2 most common variables for these sigma notation problems. So n equals 1 to infinity of 2 to the n. All right, this example, hugely, hugely, hugely important. I'm going to spend some time here. Okay, so I want to find the infinite sum if it exists. One of the best strategies when you're first beginning these is to expand the series, expand it out. What do I mean by expand it out? I mean plug in 1, and then plug in 2, and then plug in 3, and then plug in 4. So really this series is the same as when you plug in 1, you get a half. Plus, when you plug in 2, you get a fourth. Plus, when you plug in 3, you get an eighth. Plus, when you plug in 4, you get a 16th. Plus, when you plug in 5, you get 1/32. Plus, dot, dot, dot. So if we were to sit here and look at this series, there's a few things. First, we can look at the sequence and see, oh, look, the sequence is getting smaller. That's going to factor in. The sequence is getting smaller and smaller. It looks like the sequence, based on what we did in the last section, is approaching 0. It's very good. So we are going to use that in a minute. But another strategy, once you've expanded it out, is to find the sum, find the partial sums and see what they're doing. So find partial sums. We're going to get away from this strategy pretty fast because we're going to have a lot of other better strategies. Here's what a partial sum is, though. You do need to know this. That just means if you see s with a little 1, that means the sum of the first term, which would be 1/2. The first term plus nothing is just the first term. But what about the second partial sum? That would be 1/2 plus 1/4, which is 3/4. So 1/2 plus 1/4 is 3/4. What about the third partial sum? Well, the third partial sum would be 1/2 plus 1/4 plus 1/8. And what does that equal? That equals 7/8. Let's do one more. The fourth partial sum. would be 1/2 plus 1/4 plus 1/8 plus 1/16. So essentially, it's the third partial sum plus the next term, which would be 15/16. So we can take a look at what these partial sums are doing and see if the partial sums are approaching a value. So the question to ask, do these partial sums approach a value? If they do, chances are that's what the series converges to. And yeah, it looks like we're getting closer and closer to 1. So I'm just going to put here, looks like it equals 1. So my guess, and obviously we're going to establish a better way to do this in a minute, is that this infinite series converges to 1. That's what it looks like. And it does. We'll find out why in a second. But let's look at this other example and see if we can kind of establish why one of them does one thing and the other one does the other thing. So same deal, we could expand this out. 2 to the first is 2, plus 2 squared is 4, plus 2 cubed is 8, plus 2 to the fourth is 16, plus 32, plus on and on and on. Same strategy. Let's find partial sums. So the partial sums here, the first partial sum would be 2. The second partial sum would be 2 plus 4 is 6. The third partial sum would be 6 plus 8, which is 14. The fourth partial sum would be 14 plus 16, which is 30. And look, the partial sums are not getting closer and closer to a value. They are getting bigger and bigger and bigger and bigger. So do these partial sums approach a value? No. This series just keeps getting more and more giant. So this is a case where it looks like this series diverges. Looks like this series diverges. And it does. And we will find out why in a minute. So we have an example of a converging infinite series and an example of a diverging infinite series. So the question is, how did we know which one did what? So let's look at some examples, and I'm going to give you a pretty important strategy. But I'm hoping you're starting to see how we can begin to determine whether it's going to converge or diverge. So let's go to one that's totally random. How about, let's use k this time. 3k plus 1 plus 1 all over k plus 2. From k equals 1 to infinity. All right, I'm going to hit you with a lot on this one. This is a very, very good first problem for determining whether an infinite series converges or diverges. So the question would be something like, determine if the infinite series converges, or diverges. Notice I'm not even asking you what it converges to. That's a whole other thing. All I care about is, hey, does this infinite series converge or diverge? So you can go back to the previous strategy and expand out the series. For now, I'm going to show you a better way in a second. But again, you're going to get lost on some of these. And sometimes the best strategy is just to begin writing out the terms and see if you can get a handle on what's going on outside of sigma notation. So for the sake of time, we plug in 1, we get 4/3. Plus the second term would be 7/4. Plus the third term, 10/5. Plus the fourth term, 13/6. By the way, small point. I didn't simplify 10/5. Don't simplify in this case. Leave things unsimplified so you can start to recognize patterns. If I had written 2 here, that would be confusing to see a pattern, because sometimes I'm not going to start you in sigma. Sometimes I'm going to start you here, and it's our job to find the sigma notation, which is difficult. So don't simplify. That's later, but a little note for now. Okay, so we have this series. Now we could do the thing we did last time where we find partial sums and see if the partial sum is approaching a value or not. But there's a better way, and that's the whole first thing we're about to do right now. So this is a key problem to start us off. And essentially this is this is the main point of this whole lesson, apart from learning about what a series is. Is there a better way to do this? Yes. Instead of trying to think about partial sums, let's take a look at the sequence, which means the individual terms, and see if it converges / diverges. And that's what we did in the last section. So the way to do that is to take the limit as n approaches infinity. Sorry, k, because we're dealing with k in this problem, not n. K approaches infinity of 3k plus 1 over k plus 2. And based on what we did last time, I'm going to save myself some time. It's 3, right? It's the end behavior, same power on top and bottom. It's just 3. So the sequence converges to 3. The sequence converges to 3. But I didn't ask about the sequence. I asked about the series. So this is where you got to stay with me, because this idea is crucial for going forward. Think about if you were to write out every single term of this series. So you get the next term plus ... plus ... plus the next term plus the next term. Well, if each of these last terms is 3, pretty much every time you add to this series, you're just adding another 3. So if you go to like the 999th term, that's 3. If you go to the 1000th term, that's 3. If you go to the 1001st term, that's 3. If you go to the 10 millionth term, that's 3. If you go to the billionth term, that's 3. What does that mean in terms of the series? Is the series ever approaching a value? No, because you keep adding 3. You're not adding numbers that are getting smaller and smaller. You're adding numbers that are getting smaller and smaller, but approaching 3. The value is never less than 3 that you are adding to this series. They're always slightly less than 3, but the point is you're adding values that are essentially 3, like the last term. So I'm going to say this, the last term is 3. So what does that mean for the series? That means the series can't converge because you keep adding 3. Every time you go out farther and farther and farther, if you were to do your partial sums, you just keep adding 3, basically. So the series diverges. This is an example where the sequence converged, but the series diverges. This is a hugely important process that has its own name, and it's on the sheet I'm going to give you later. This is called the test for divergence, also known as, so AKA, the nth term test. And here's what it says. It says, if I give you an infinite series, look at the sequence. If the sequence diverges or converges to a number that is not 0, then the series diverges. So if you do the sequence analysis and look at what the sequence converges to, if you get 0, that means something. But if you get anything besides 0, that means diverges. So if you get a number or you get infinity, that means diverges. That's the huge part of this first kind of lesson after getting used to what a series is. So I'm going to show you how you would formally go through this. So check this out. So an example, another one. Let's say how we had this one. N equals 1 to infinity n factorial over 100 to the n. Okay, so I want to know, again, all of these questions are, does this infinite series converge or diverge? And again, we're talking about series, not sequences. But here's how you're going to do it. You're going to look at this and really remember back to, okay, the sequence. Let's start there. If we were to analyze the sequence, what does the sequence do? So in my mind, I would think, look at the sequence. So the sequence is where you just look at it term by term. So n factorial over 100 to the n. And let's specifically look at what the last term, or in other words, whether or not the sequence converges or diverges. And this is from the last lesson. So this really builds on that growth rate idea I talked about in the last lesson. What does this sequence do? Well, From last lesson, we know that factorials grow way faster than exponentials. So this sequence diverges. It goes to infinity. This is a very nice thing in this case, because if this diverges, then we would say by the test for divergence, the series also diverges. Now we can go back and look at this problem from earlier. It's exactly what happened here. We had a series that consisted of terms that got bigger and bigger. If we just looked at the sequence and said, what is the last term? There is no last term. The end behavior of this is infinity. Well, if you keep adding bigger and bigger numbers to a series, the series is not going to converge. So if you just keep adding numbers that are bigger and bigger and bigger, the series is not going to converge. It's going to diverge. So in this case, same logic. If the sequence diverges, the series diverges. That's essentially what we are doing in this section. Let's do another one. So how about this one? 5n squared plus 2n minus 1 all over 3n squared minus 4 from n equals. Now, by the way, I could start the bottom at any value. If I started at 1, you're going to get negatives. That's really weird, and we don't want zeros in the bottom. So I can just say, all right, start this one at 2 and infinity. All that's changing is I'm starting with a different first term, but it still goes to infinity, and I don't even care what this converges to. Meaning if it converges, it has to converge to a value. But we're not worried about that in this section. All I care about is, does this series converge or diverge? And that's it for now. So same logic, okay? So we're going to look at the sequence. So instead, we're going to think about what is the last term of this sequence. That was a pretty terrible infinity. Let's try that again. So limit as n approaches infinity of this sequence. So what does the sequence go to? Well, this is where, again, you need to know your end behavior rules. And since the powers are the same, we look at the coefficients, and it's 5/3. So the sequence converges to 5/3. But what does that mean for the series? Remember, these are two different questions. The sequence, that means the last term is 5/3. But what about this series? Well, by the test for divergence, we can show that I just found the limit as n approaches infinity of my original, which I'll rewrite it again. So 5n squared plus 2n minus 1 over 3n squared minus 4 equaled 5/3. Does that mean the series converges? Absolutely not. Because remember, the only thing that we want to see happen in order for the series to possibly converge is get 0. And this is not 0. In the last one, this was not 0. But in this one, even though we got a number, which means the sequence converged, it's like we're adding more and more numbers every time we try to find the series. So this is a case also where the test for divergence did not give me 0. Therefore, the series also diverges. This infinite sum does not exist because we keep adding bigger or values that are not approaching 0. That's the key. We're not approaching 0. So one more example. Which one do I want to do? This one. And then I'm still avoiding one last question. We're going to handle it right here. So n equals 1 to infinity. Okay. What on earth about this one? This is a little weird, but it's not, because I told you a shortcut for dealing with cosine and sine in the last section. Remember, cosines and sines are essentially 1. Now, for finding the actual sum, this sheet's not going to work. We're not going to actually find the sum of a lot of these. We're just going to have to determine if it converges or diverges. Is all we care about. So we can kind of compare this with this series instead. It seems like a cheat, but we're not trying to find what it converges to. All we care about is, does this converge or diverge? And when we're dealing with sines and cosines, they just oscillate between -1 and 1. So they're not growing. That's a key. They're not getting bigger and bigger and bigger. They're just fluctuating. So we're going to compare this. Now, this is probably the most important thing I'm going to say as in terms of how to deal with something in terms or working with a test for divergence. Here's what we're going to do. All we're going to try to do is, again, determine if it's converging or diverging. So let's do the same strategy, And let's look at what the sequence does. Well, what does the sequence do? Well, top's not growing, bottom is growing. This is an obvious case where the limit approaches 0. That means the quote unquote last term, if you were to expand this out, you'd get 1 plus 1/4 plus 1/9 plus ... And here's the key. The last term is 0. You are adding terms that are essentially 0 at the back end. That means something significantly different than the other two. That means that the series, ready? Who knows? You cannot make a conclusion. No conclusion can be made yet. That's what the next sections are about. So no conclusion from the test for divergence. The test for divergence was not the strategy to use here. There's something else going on. So if you ever get 0, you can't say it converges. I see it every year. Like I'm in Groundhog Day. Every year I will see students say, oh, it converges by the test for divergence. You should never say converges because the test for divergence said so. This is cringy to me. If you say, oh, well, the test for divergence showed me it converged. That's awful. It makes no sense because the test for divergence only does one thing. It shows you if it diverges. And you know it diverges if you get a number or you get infinity. But if you get 0 when you're looking at the limit, you only know one thing. You know the sequence converges to 0, but that tells you nothing about the series. Even though you may think, well, wait, aren't these terms getting smaller and smaller? Yes, but sometimes they don't get smaller fast enough. And that's one of the major keys that we're going to be looking at in the next few sections. So for now, it's actually pretty straightforward. When you're doing your homework, if you have a series that either diverges, or sorry, the sequence diverges, or the sequence converges to a number, you're done. The series diverges. If you have a series where the sequence converges to 0, you don't know. You just say, Ms. West, I don't know yet. We have more work to do. Okay? And that's it. So the test for divergence is inconclusive if you get 0. Otherwise, we know that the series diverges by the test for divergence. All right, that is it. That's a long one, I know. I'll do a fast version of it, but this is a lot. This is key stuff that you really, there's a lot going on in this one that you definitely have to know how to do if this section is going to make any sense to you. All right, that's it for now.